Big welcome to everybody to today's webinar. I'm super excited. We have more than 215 participants by now. That's really amazing. A big thanks for you all for joining us today. We all know you have a busy agenda and we hope to make these next 60 to 90 minutes worthwhile for you. Let me just get the slide sharing going. So let's have a look at what we have planned today for the webinar. We will start with a brief introduction to who we are at Sphere Energy, because I think not everybody knows us by now. Then Ulrike will tease some of the key findings of our solid-state battery white paper that we will publish next week. So some cool, interesting insights here. And then for the next 30 minutes, we will have the three invited panelists, Francisco, Raimund, and Jürgen, present their technologies, focus areas, and their companies or respective working groups. And then in the end, we will have and make use of this opportunity of having these experts in a virtual room together here today and ask them as many questions as we can. And I really would like to encourage you to do so and leverage the chat to ask what is interesting to you to discuss. So we hope you all get some interesting takeaways out of these next 60 minutes. Maybe before we start, some housekeeping. You're all muted. Your videos are turned off, but you can post questions in the chat. There's a little chat symbol in the top. And we will try to answer all these questions in the session, in the panel session later. And we'll make sure that we follow up with emails accordingly to those of you who stood unanswered due to time reasons. So I would say let's start with a quick introduction to today's panel. First, we have Francisco Carrazza with us. He's the CEO of Buzzworld, and he's one of the most, working on one of the most promising technologies in the solid-state battery field. I'm sure we'll get to know a little bit more details on what technology he is working at Buzzworld. Francisco has tons of experience in the industry, and he's been working, I think, for more than 10 years as a managing director at Nissan. So this guy really knows what it needs to succeed in the industry and what are the long journey to make a commercial product in the EV space in the end. Next, we have Raimund Körber. Raimund is one of the, I would say, rising stars in the battery industry and is currently leading the innovation activities at Factorial. I personally believe that Factorial is amongst the most advanced solid-state battery manufacturers out there, and I'm super excited to learn more about his vision and also about his challenges ahead. Thirdly, we have Jürgen Jannik with us. I think Jürgen really doesn't need a big intro. I'm sure there is not one person here today with us who hasn't read at least one of your papers, Jürgen. I think that Jürgen is arguably the most or one of the most experienced solid-state battery professors out there. And what I value, Jürgen, is always that you're looking at things from a different perspective, as we have seen in your latest publication, from almost solid-state to all solid-state batteries. I'm super excited to have you with us today, especially keeping us honest when we may be getting a little bit overwhelmed with the potential and the exciting things of solid-state batteries and of this technology. Thank you all for taking the time to be with us today. That's really not something that we take for granted, and really happy to have you with us on the panel. Finally, we have Ulrike and myself who will try to moderate the session a little bit, coordinate the questions, and address the topics accordingly. So let's get started. Let's get started with the introduction to Sphere. We are a technology service firm operating out of Paris, Zurich, and Augsburg in Germany. We have a diverse team of scientists, engineers, data and industry experts, and our goal is really to help companies leverage this battery technology to grow their business. We do so in three different service categories. We are, on the one hand, building new test equipment to access really all the relevant information from new technologies that are often come in formats like pouch cells, for example. The second service we are offering is our battery testing and performance validation. where we look at how batteries perform under various conditions and build relevant data set for your BMS, BTMS, and simulation models. And thirdly, we have our consulting services, where we mainly focus on innovative technologies, operational efficiency, or sustainability topics like the CO2 footprint of your batteries. At Sphere, we work along the entire value chain of a battery company. We work with R&D departments, we support innovation teams, the product engineering, and also work with C-levels on the strategic topics to really make the most out of this amazing technology. Our projects come across industry and deal with many different challenges, and I believe that this is also really what makes us valuable for our clients. We always look at it try to look at it from a holistic perspective, where we combine a scientific approach and what is really needed to make a product work in the end. And here you can see some of the examples of projects that we have already delivered, some more on our website. And obviously, if you want to reach out to us, do that via our website or via email. And one thing that is always in the back of our mind are new technologies and the potential of those. And such technology is clearly the solid state battery technology. And since new technologies always have somewhat something from a holy grail and a money drain at the same time, and especially this technology, we decided to put together a white paper where we look at this technology really from a fundamental perspective, but also shine some light on the challenges in the long road ahead to commercialization. And at this point, I just wanted to mention again that we will publish this article next week. So stay tuned here. And in the next part of this webinar, Ulrike will dive a little bit into into some of the data points and some of the key points that we will showcase in this article. And with that, I will hand over to you, Ulrike.
Thank you, Lucas. Thank you for the opportunity to speak a bit about this new white paper. Thank you also all of the other panelists to join and chime in with their input. I will try to be brief on this part, just to leave as much space as we can for Jürgen, Francisco, and Raymond. So we thought about starting with why solid state, because there is a lot of confusion, in our opinion, on why we are trying to use this chemistry essentially, and we will explain also a bit better what is solid state later. So the idea of a solid state usually is sold, if you want, as a technology which can improve energy, but is not per se true, I would say. So a solid state cell is not intrinsically more high energy. Some of the other active materials which compose the cell, which can enable higher energy. And for example, by utilizing lithium metal, that's where we would have a huge increase, but it is by no means solid state exclusive. And here we also report some of the important KPIs to consider to make a competitive cell, because it's important to remember that what's on the solid state will compete with what is on the market. So a lithium-ion cell, which today state-of-the-art is around 270 watt-hours per kilo, 700 watt-hours per liter. But we have already higher energy cells coming to market, which are being trialed in automotive and are going to be in vehicles very, very soon. So you can take a look at the KPIs, but don't focus on those on the right, because you can read more on the white paper. In our opinion, what will be a huge potential improvement of a solid state will be some opportunities to simplify pack design. And that's why we are very much interested in this technology, because solid state means replacing the electrolyte, and some electrolytes might enable performance in a wider temperature range, which again needs to be confirmed at large stack level and pack level, most importantly. But this could lead to important reductions in cost at system level, which is what we really need to consider. So not the cell or material performance, but really the overall application performance. At the same time, we wanted to highlight on this slide that, although some solid state might be safer, for example, like oxide type, some polymer type, in our opinion, there are still a lot of safety challenges that need to be understood and well characterized. So in principle, solid state might be a safer alternative, which can enable, again, materials such as lithium metal, but at the same time, they might pose new challenges. For example, they might hydrolyze or undergo combustion as well. This is by no means impossible with solid state, because in the end, you have to remember that regardless of what you're looking at, we are dealing with a high energy device. The last important opportunity, in our opinion, is this option to enable new positive and negative electroactive materials. So we are looking at lithium metal, for example, or silicon-based, and solid electrolyte might be a very good opportunity to go there, but at the same time, we are also looking at some maybe low cost or very high energy positive electroductive materials, such as manganese rich. And again, you'll be able to know a bit more and read a bit more beyond our rationale in the white paper. If you go to the next slide, Lucas. What we wanted to discuss and clarify is what defines solid state. So the solid state is defined by the electrolyte, which is just one component. And this slide is I use quite frequently. It's busy on purpose just to showcase how many alternatives we have in terms of material components. And by no means this is comprehensive. So this is just a focus on the cell, on a pouch type. We can have different cell designs and so on, and so many materials. So solid state means using, in our opinion, a truly solid state, either a fully solid state polymer electrolyte or a solid inorganic electrolyte. And for this session, we'll be mainly focusing on the polymer, I would say, from an industrial point of view. The point is that very often we see things mixed up. We see, for example, lithium metal cells called solid state. We see claims saying that solid state will always be higher energy, and things like that. Is completely wrong and generates a lot of confusion. And just to highlight how different things can be, even though some categories can be similar, that's why we thought about inviting two promising emerging players in the field of polymer electrolyte development, just to showcase how different some technologies can be, even though they might seem to be in the same category. And if you go to the next slide, Lucas, in reality, we have a lot of products and categories to consider. So again, quite busy slide, and the I would say categorization can be discussed. Is just what we are proposing. But in reality, to really distinguish different technologies, we have to consider all these categories, if you want. So you can have thin film batteries, for example, which are already commercial, but they're not for automotive. They're just in niche applications. What we're interested in is bulk cell types. So similar to, I don't know, a large 30 ampere hour pouch. We can have different types of stacking internally. One of the end games sought by some players is the bipolar stacking. And then we have a lot of different just electrolyte chemistries. And if you remember the previous slide, you can imagine how many combinations in principle we could create. It's nearly infinite if we think about it, because for every new material, we might have new issues, we might have new variables to consider. So generalizing is one of the main problems in our opinion. And that's why we have to be very, very careful with what we read, with what we assess, and with technologies that we consider essential. And if you go to the next slide, you can see we talked about just introducing two technologies which in principle might be similar. So we have Prologium, which is targeting with one of their products what we say cell is pack. So it's a single block of a cell stacked as a bipolar cell. essentially the main electrolyte type is oxide, as far as we understood, although most probably they are targeting to use some catholyte in the beginning. But here is just to show that, you know, this product which is not commercial, but which would be very challenging to commercialize. And the idea is to make a single pack, which would, for example, power an entire EV or an entire product. And if we go to the next slide, on the other hand, we have, for example, General Motors, which last year showcased a new product using a gel type polymer electrolyte. So it's the same concept, if you want, is a bipolar stack, but they're going to implement it initially for a 12 volt module. So essentially replacing a lead acid battery inside a car, not for traction. So even though these technologies might be somewhat similar in reality, they might be targeting very different applications, and then they will have very different issues. And it's something that we try to uncover a bit more in the white paper. And this is just two very brief examples. And if you go to the following slide, again, trying to be as brief as I can, and then Jürgen will be diving, I think, quite a bit more, and it's probably better suited than me to talk about some of these issues. If you press again, Lucas, sorry. The point is that even though solid state might seem mature, might be touted as being commercially ready or being in the market soon, we do have still a lot of fundamental issues also still to solve. So I hinted at some of those previously. For example, at the system level, we still don't have, I think, data on larger cell stacks and on performance system level, on thermal behavior and safety aspects. But at the same time, we still have a lot of issues at fundamental levels, on materials level. And in our opinion, the key is solving issues at the interface between materials. And then, of course, we have a lot of other considerations to make, which you can find in the bottom of the slide. Again, you will receive the material, so you will be able to read and go through it. But for example, going to processing mass manufacturing, considering end of life, these all very, very, very challenging. And if you go to the final slide for my section, I already saw some questions in the chat and in the Q&A asking where is solid state. By now, hopefully you understood that we have so many technologies that it's hard to generalize. Each technology will have slightly different KPIs, slightly different properties, and might be targeting different applications. So it's really hard to tell you where we are. What we can tell you is that we are not yet at the market for mass market TV. We are not yet at the market for mass applications in general. What we have seen, for example, is from Bolloré, a very mature cell, which is, however, lower energy than current state-of-the-art lithium ion, but has been applied successfully for heavy duty and bus applications, essentially. But the rest, as you can see, is still very far. And sorry, thank you. Yeah, thank you. And what we want to say and what we want to showcase with this slide is that it's very hard to get to the market, essentially. So moving from a research lab to mass manufacturing can be a very lengthy process. And going through automotive qualification is really, really complex. You have to go through a number of designs. The requirements are very strict, and most importantly, you need to reach mass manufacturing. So you need to produce cells on a large scale, on a gigawatt-hour scale, which today is not done, and also for its subcomponents, for the most part, is not done. So today we can see that most chemistry are at different technology readiness levels, so they are at different stage in automotive development, and no truly solid state is too close to reach the market. And again, you'll be able to read more about our opinions in the white paper, where we assess some of these players that you can see on the screen, and many, many more. Having said that, without further ado, I will hand over back to Lucas. Thank you.
Perfect on time, Ulderico. Thanks a lot for these insights. And as Ulderico said, next week we will release the white paper on our LinkedIn page, so stay tuned for that. And now I would say let's hand over to our panelists, starting with Francisco, to share a little bit what he and his team are doing at Buzzworld.
Fantastic. So while I'm sharing the screen, how do you want to do, Lucas? So we do the presentation and there's Q&A at the end, right? So yes, at the end of the whole presentation, not just each one. Correct?
Yeah. So people, if you share your Q&A in the chat, then we'll come back to that when we do the panel in the end.
Perfect. Fantastic. Briefly, so I will do it quickly so we have time for discussion at the end. So this is the situation of the industry and the context in which we launch our company Basketball. So in our company, we are mostly from car industry, and myself have been working, as you said before, at Renault Nissan for many years, preparing the launch of electric cars since 2008. So quite a long career in electrification, trying to understand and figure it out. What is this industry needing to succeed in the electrification of the sector? And one of the key learnings is that we are still far away from reaching the actual parity between combustion engine vehicles and electric cars. And there are many types of parities, right? So there's a retail price parity from the customers, there is a TCO parity, and there is a profitability parity from the OEM point of view. So in each of those, we are not there yet. What we need to be to ensure that this industry is self-sustainable from the economic point of view, right? So that we are no longer needing subsidies from the government to boost the demand. And that's in our opinion, that's the role of solid-state batteries. So this is the first mission that we have given ourselves, is developing a technology that is capable of or helping this industry to become as self-sustainable, economically speaking, as possible, as quickly as possible. So overall, what we see, and this is clearly something that everybody understands, right? So we have seen a lot of estimates about the size of the market, and with huge number in terawatt hours and so on. Our view is the only way this is happening is if we are capable of making batteries that are answering the expectations from our customers, and from the end customer point of view, from the price, obviously, and from the performance of the battery. So the way we see our goal at the end of the line is the market is needing much cheaper batteries, much smaller batteries, much lighter batteries, obviously much easier to produce and much cheaper to produce, which is a huge challenge for current lithium batteries, and without forgetting the footprint from the sustainability point of view, right? So the society is expecting and is demanding that whatever we do, we consider seriously CO2 neutrality moving forward. So looking at all these challenges, this is like the first line specification when we created the company, right? So this is what we need to achieve as a company. So we started from the point, we started from the technology that Michel Armand has been developing over the past year with his team at the CIC Energy Gune, that has been focusing on improving the solid state and the gel polymer electrolytes for the past decade. And I share with you guys here a few pictures about what CIC is with laboratories. So I think now they are hitting probably the 200 researchers in CIC. So it's clearly our research arm as a company, and we are working with them quite closely to keep improving the type of polymers we are using. So overall, when we were looking at the different type of solutions that were available in the market, we chose the polymer because of the specifications I was mentioning before. So clearly we need a solution that is bringing a significant cost reduction versus current lithium-ion batteries, this is one of the main drivers for the market adoption, right? So you need to get your electric cars at the same retail price as the petrol the petrol version. And if we are not capable of reaching that, the market is going to have a hard time taking it off. The way we are doing that, or one of the ways we are doing that, is by reaching a very high energy density, while at the same time we are reducing the capex that is required for production, and we are reducing the energy consumption and the CO2 footprint by using polymers that are compatible with the existing gigafactory equipment. And the goal is being able to reduce the risk, de-risking the switch to technology by developing a process that doesn't change the traditional equipment you use in a gigafactory. From the moment you are bringing a new technology and a new process and a new equipment, it's too many risks in parallel are going to prevent you to scale up your industrialization as quickly as the market is expecting. At the end, this is what we are landing at the moment in our company. So we are targeting to reach the 1,000 watt-hours per liter and the 450 watt-hours per kilo. The operating temperature is pretty much the same as for traditional lithium-ion batteries. Pressure is pretty much the same as traditional lithium batteries. And cycling, our goal is to exceed the 1,000 cycles. It's typical for the automotive application. The key barrier, or the key, let's say, difference from the polymers and lithium metal is always the C rate. From the moment you are demanding a power application, the technology is going to have challenges to deliver. So with the technology we have now, we can ensure 20 to 30 minutes fast charge for the automotive applications. That is enough for the mass market solution. Obviously, if you're looking to address the premium car segment, they're going to be much more demanding in the fast charging. So overall, this is giving you an idea of the type of technology we have at Basketball, and a little bit the origin and where we are heading as a company.
Amazing, Francisco. Thanks a lot. Really, really great insights, not only from a technological and market point of view, but also where you guys stand as a company. It's so fascinating to see these projects now grow. And we just talked in the previous prep session about the growing team you have, and really amazing to see such a successful story here in Europe. Thanks a lot again. And with that, I would hand over to the next industrial panelist we have, Raimund. If you want to share with us where Factorial is and talk a little bit about the technology you guys have at Factorial.
Yes, of course. Just put this on the screen here. No, that's not the right one. Can you see the slides or the presenter mode?
Presenter mode for now. Usually it's swap displays, but yeah, there we go.
That's fantastic. Yes, so first of all, thank you for the invitation. Thank you for having me here, and also thanks to the audience. So we have like over 300 participants and already a couple of questions. I just briefly want to introduce Factorial Energy to those of you who don't know. We're a US-based company near Boston, cell manufacturer in the solid-state battery space. Just briefly, I have to show this disclaimer. Shows we're growing as a company. Things are getting more serious. Yeah, I really like the point that Ulrike mentioned before about the technology readiness level and how long it takes to develop different technologies. So I want to briefly touch on the timeline that Factorial has been through. To those of you that don't know Factorial, the company emerged from a parent company that was called Leo Nano. The company was founded in 2013 by two very smart people from Cornell University. But they started out as a cathode active material producer, which then over time, exactly this time span, was incubating a solid-state battery technology based on a polymer electrolyte. And I think it's very clear you have to not only develop the technology, but you also have to work on scaling up. And today the company has over 250 people. We sample 20 to 100 amp-hour cells to our customers, which I will talk about a little bit later. But the message is it takes time, and you need a lot of work to get where we are. And So what do we will do? The technology is based on a polymer electrolyte. Jürgen would probably call it more like almost solid or quasi-solid. So we not only replace the electrolyte, but we also replace the anode part. And I think this picture shows very graphically what this does. So it reduces the overall necessary space for the same energy to a smaller volume. So the graphite anode is, of course, has a much bigger volume than the respective lithium metal anode. The cathode in our case remains essentially the same, so very much unchanged. And this yields a system which has not only a higher energy density, but also very good power and presumably higher safety. So from an energy density standpoint, you do not only increase the volumetric, but also the gravimetric energy density quite significantly. And in respects of safety, it's very important to mention the thermal improvement. So when you compare conventional lithium-ion batteries, you use something like ethylene carbonate, which has a flashing point of maybe 15, 17 degrees. And then you add a couple of flame retardants to eventually reach 60 or 70 degrees for flaming point. So our technology is thermally stable up to 200 degrees, which might not sound like a lot, but it's a huge improvement from automotive point of view. Cathode side, as I mentioned before, we use commercially available materials, pretty much off the shelf. Currently, we work with NMC 811, but we've also tested beyond that. And the last 2 points, I think they're very important. It's essentially the same, but we can leverage existing lithium-ion battery equipment, and we think that we can use 80 to 85% of the existing battery production process, which is huge because it overall de-risks our technology introduction, and we can use existing equipment. We don't have to develop it ourselves, but we can make adaptations here and there. With the biggest change, of course, being the lithium metal anode. So this is the part that changes in this case. This technology has received a lot of attention over the last few years, and we have attracted a couple of commercial OEM partners. Currently, our 3 public partners in the automotive space are Mercedes-Benz, Stellantis with all its brands, and Hyundai Kia. And they also are investors in the company, and we have joint development agreements which run in parallel to develop a cell for their automotive application. Yeah, and I'm looking forward to the discussion and hopefully some interesting questions.
Thanks a lot, Raimund. Fantastic. Very advanced. And as we could see, it's not something that you develop overnight. We could see the timeline from Raimund already, what took them a couple of years to get where they are now. And I think there is still a journey ahead, but awesome insights. And now I would say, let's move a little bit more to the fundamental side of things. Jürgen, happy to have you on board as well today, and really curious what your introduction will be about the fundamentals of solid-state batteries. I think you're still maybe muted.
Yeah. Thank you, Lucas. Can you see my?
Yes, if you now
screen, very good.
There we are.
Okay, yeah, thank you, Lucas, and to the others to having me in this round. It's of course a great pleasure. I always love the exchange with industry, because in the real world there is lots of scientific problems, I would say, to be found, and then of course to be tackled. So I'm working at Gießen and also have a team at Karlsruhe Institute of Technology, and I would say I'm always get a bit of teeth ache if I'm named as a battery professor. So I would say I'm a physical chemist who works in the field of electrochemical material science. And well, if I were a company, then of course I have a bit to advertise my group or my teams. So I think we are really a pure university group, so not operating at one of the huge national research centers. So I think we are flexible because we have a quite high turnover frequency for young scientists, and that also defines our major mission. Our major mission, of course, is the thing I really like to highlight, that is education and training of young scientists. And this is for sure the biggest impact we have to industry and the society. And I think this happens, of course, through the understanding of physical chemical phenomena. So this is one of our tasks. Being quantitative. I think physical chemistry is that subject in chemistry that is always annoying many of the students, because we always insist on numbers and on reliable numbers. And of course, exploring thermodynamic and kinetic limits. And so I think we are quite an incubator for future team leaders in academia and also in industry, like Raimund, who got his PhD in Gießen and are well linked. And I think we have a broad spectrum of research subject that is solid state concepts in electrochemistry in general, advanced analytics, and we try to bridge electrochemistry and physics, which I think is quite important, and of course to look for sustainable materials. Now, if I would aim myself for the best battery, I would need to run a company, right, guys? So my team rather aims to understand the barriers on the way to better batteries. So, but in order to do that, we focus really on realistic materials and cell concepts and try to make reliable quantitative studies. I think this is really what is our mission. Now, there is one problem with that in the battery field. Often communication between industry and academia is a one-way route. Industry often thinks, well, they get all the information from us, but they don't tell us really what are their real worries and sorries. So if there is complaints about what academia is doing, well, give us more information of what you need, and then you will get better answers. And I think, honestly, the beginning of new developments still happens mostly in academia. Think of sodium, the sodium electrochemistry, of course, started in universities, solid electrolytes. The major trigger, for example, for the solid electrolytes was a paper by Richu Kano at Tokyo Tech University. So, and also something that don't take this as too serious, but not always industry does know everything better. Just remember the decision in industry to forget about lithium iron phosphate some years ago and all the decisions following that. I think these were industry decisions, of course. So I have learned to try to make my own opinion about things. And we do that on the basis of clear-cut experiments where we do often own materials, both in Karlsruhe and in Gießen. We make own cathode materials, all the electrochemistry, and then we have a quite, would say, elaborated bunch of analytical experiments where we can look into cells and try to make in situ, even operando measurements to understand what is going on in cells, hopefully as close, I would say, to systems that may be applied or are even applied. And this then leads us to the analysis, I would say, of challenges. So this is from one of the most recent papers, which I published together with Wolfgang Zeyer from Münster University, also was in Gießen quite a while. And this brings me to the point, kind of, would say, short-term conclusion that when it comes, and don't be afraid, on the next slide, I will ask, okay, what do I understand as solid-state battery? I would say a bit loud-mouthed. I would say the high-rate, reversible, and long-term stable high-capacity anode, in brackets like lithium or silicon, at low stack pressure still has to be demonstrated, as well as large area dendrite-free thin separators, solid state, for high-rate operation still need to be demonstrated. And I'm happy for any demonstration that can be reproduced and that is reliable. High capacity and high rate long-term stable cathode composites at low stack pressure still need to be demonstrated. Now, on my next slide, you will see, and I already see worries on Francisco's face. This is, of course, very much from a kind of inorganic point of view when it comes to polymers. And this is, of course, one of the next things I like to make. Things become a bit different. And so this is from our, I would say, appeared just a few days ago, but a little, very short paper, almost a pamphlet, I would say, which is titled From All Solid to Almost Solid State Batteries. What you see at the left side here, so let me go to the pointer. What you see on the left side is a typical cartoon of a lithium-ion battery, as you all know it, with liquid electrolyte. So let's say about 25 to 8% liquid fraction, with all its advantages and disadvantages, and of course even with the, and I think if we take Francisco's numbers as true, still being too expensive. And well, and then I would say in 2012, there was a publication by Richard Cano publishing a thiophosphate electrolyte, so a ceramic electrolyte that showed a very, very high ionic conductivity, and that triggered the belief that solid-state batteries will come. And at that point, people thought of all solid-state batteries where one would enable a lithium metal anode, would use a pure solid kind of ceramic separator, and of course then a ceramic composite. And I think the late 2010s brought much better understanding of all the related issues and challenges. And there were two parallel developments. One was in fact that this industrially, because this is really difficult, of course, there is companies following that, but there is quite a bunch of other companies, I think, like, for example, Francisco, going the way from lithium-ion batteries to gel polymer batteries, where you gellify the liquid electrolyte and get some advantages out of that. Now, I wonder, Francesco, whether that is in fact, whether this is really 30% cheaper. I think I would love to have a discussion on the price for that. If I go from here to there, adding polymer, whether that can get cheaper. Now, the other way is going from all solid, I would say, to almost solid means, okay, trying to mitigate some of these issues, contact issues mostly, and the chemomechanical issues, by adding a bit of liquid. I would say a kind of contact glue or mechanical mediator that may allow then to operate a cell which has really just a bit of liquid and is more on the solid state side, whereas this, I would say, a gel polymer cell for me is in principle a lithium-ion battery with a bit of polymer that jellifies the liquid electrolyte. It's maybe a bit less liquid electrolyte, but maybe there's advantages of safety. I think this is something definitely we can discuss. The problem is all that is being, well, all these three cartoons to the right are considered as solid-state batteries. Huh? That makes a part, I would say, of the misunderstandings in the world. Industry has to do something that works at the end, and probably what will work is somewhere here in between. So, and the question simply is, what can be manufactured in a cost-efficient way and what will have economic success? I think it is very difficult to get a full all-solid-state battery into operation. Well, I think it's not impossible, but very difficult. And final slide is just saying one of the issues, of course, which is really may be critical for any ceramic or inorganic part in a battery, and that is this conductivity chart, which is part of our recent perspective. What you see here is a typical picture shown in semiconductor industry, lithium mobility, lithium-ion mobility as a function of lithium-ion charge carrier density, so concentration, and then the product is conductivity. So these lines are isoconductivity lines. And the highest conductivities, about 10 millisiemens per centimeter total conductivity, have, of course, liquid electrolytes and the sulfides, the ceramic materials, but at the cost of a factor of 20 higher lithium concentration in then 30 to 35 volume% of the battery. So this is, of course, well, when it comes to resources, may be an issue. And this is the reason, of course, why at the same charge carrier concentration, polymers are attractive. However, true solid electrolytes, true solid polymer electrolytes have a too low conductivity. That's why you gellify them, or you bring in solvent to make gel polymers, then have this higher conductivity and then allow the construction of batteries. So that's it. This work, of course, we do is not all done in Gießen and in Karlsruhe, but we are part of a big team, big German cluster funded by the Federal Ministry with more than 180 scientists, the FESTBUS cluster, and I think I'm really grateful to the Federal Ministry to support us so generously that we can do the work we do. Thank you.
Thank you, Jürgen. A lot of condensed information and interesting teasing points here. And with that, I also would like to open the panel now, maybe handing over the word to Francisco. Now we heard that there is not one solid state technology. And I think this is also what people ask us a lot of times, right? What is solid state? Is it actually needed to define this term, right? Or is it like lithium-ion batteries, which is also not really defined? Lithium-ion batteries can have many different cathodes, many different anodes, many additives in the electrolyte, right? What do you think, Francisco? Do we actually need a clarification of this term, or will this just be a new cluster of or subcategory of lithium-ion batteries that is doesn't need a defined terminology?
Well, technically speaking, I agree with everything Professor Gianni had just said. So that's the truth, right? So and it is funny because the first time I was talking to Professor Armand, and I was talking about solid state batteries with polymers and so on, he was looking at me and saying, "You don't know what you're talking about." Right, so when the polymer is solid, this is not a battery; it's isolating material, right? So it's only working when it's not solid anymore. That's why we need to heat to 70 degrees to change the phase. So it is true, it is true. But then I also realized that when you're talking to the general public and the customers and investors, if you have too many names and too many things, you lose people at the first 5 seconds. So somehow solid state is a kind of envelope of a lot of type of things. It doesn't mean anything anymore, right? So it just means an envelope of different technologies that are bringing value to the battery by reducing the cost and increasing the energy density and a number of things, right? So many of the companies that are in our space, they have very little solid content in there. So I agree with everything Professor Gianni said, and it's just a buzzword has become what everybody needs to be solid somehow.
Great.
But it simplifies the message.
Absolutely,
in a way.
yeah. And when we look at lithium-ion batteries, we also don't differentiate too much, right? There is many different sub-technologies there that are coexisting.
As long as there is lithium and there are ions, it's fine.
Raimund, maybe a question to you. Why have you at Factorial decided to go the route of polymer-based electrolytes amongst these wide range of different possibilities? Maybe you can shine some light from a technological point of view where you see the benefits of this technology.
Yeah, I think, I mean, ultimately this was of course before I came, but I have good justification, I think, which is really using existing lithium-ion battery processes. It's just super advantageous. It just gets you to the market much quicker. And also I think, so having myself worked on all solid-state batteries, as you described, there are a couple of hurdles, especially in the mechanical nature of the materials. So batteries move and expand, they shrink during operation. And this is all mechanical stress. So having polymer or flexible component, even a liquid component in the system, overall improves the wettability, it improves the mechanics of the system, and the processability. So there's a multitude of reasons why this works better. But I think it's ultimately what we're trying to do is just produce a high performance, low cost battery and not anything all solid or semi-solid, or so our goal is different maybe from a more academic standpoint.
Awesome. Love that, Raimund. Thanks a lot. And maybe, Francisco, back to you. When we talk about solid state batteries, one of the key features that we want to enable with these technologies are obviously metallic lithium anodes, right? This is where most of the benefits of this technology comes from. Could you elaborate a little bit on the anode side and on the different scenarios we have here of zero anode configurations and how it behaves with the metallic anode? Because as Raimund just said, the battery is breathing, right? And with zero anode designs or with very low contents or small lithium foils here, we maybe have even bigger expansions. Maybe you can elaborate a little bit on the anode side, which is one of the most important ones in the solid state.
Yeah, I think here again, there's some kind of buzzwords, because if you have no anode, you have no cathode, you have no electrolyte, you have no battery, right? So somehow you need to have a piece of each. The key point is, how can you do to reduce as much as possible the excess of lithium? Because we know that the cost of lithium is the key parameter, right? So obviously we hope the cost or the price of lithium will continue to decrease over time, and we are on our side quite confident that it will decrease. But even in that case, you need to make sure that you put as little lithium as possible in the anode. So that's part of the key challenges we have now. not just ourselves, but we need to work with our suppliers and the supply chain to make sure that we can manufacture that anode with as many microns as possible of lithium in there.
Thank you. And Jürgen, maybe a question to you here. How do you look at the whole development, the interface, and especially the dendrite topic in these technologies from a lithium perspective?
Yeah, I think, well, we work a lot into lithium, and the dendrite phenomenon, of course, is a statistical phenomenon. And first of all, one of the problems is whenever you do lab studies, the area you investigate is typically relatively small compared to later, let's say, realistic produced areas of cells. And later, maybe just 10 dendrites in about 10 million cells can damage your business, as we saw with Samsung and their problems with the Note 7 and the short circuits across the separator. So just a few bad cells will then be catastrophic. I think it's not yet, for me, I would say I have not yet seen really a clear-cut proof that 100% large-scale dendrite-free, let's say, solid-state separators are possible. We know, of course, from the polymer batteries that at the higher temperatures, the lithium metal polymer batteries are currently being operated. It seems that dendrites are no issue, but that means also that lithium metal is operated at much higher temperature than at room temperature, and mechanical properties change. It's closer to its melting point, and that may be one part of the issue, of the solution. And well, I think these cells do not really operate at high C rates and are not charged at high C rates. So for me, this is not yet really a solved issue.
Yeah, and the fast charging topic is a very interesting one. We'll come to that in a second.
Yeah.
Let me ask one more, since we are at the internals of the cell, and we have a lot of questions about the cathode side as well. Cathode, I mean, we hear a lot of LFP noise now going on. I guess, Raimund, when we talk about high performance cells, you are focusing mainly on NMC, or how do you see your technology also fitting together with LF or other cathode technologies, e.g. LFP?
So we've tested the compliance of a lot of cathode materials with our system. So far, we do not see any limitations on the cathode side. For LFP, I think you always have to make sense on the system point of view. I think our biggest asset right now is the high energy density, so reducing the weight of the battery in the vehicles and reducing the space. So even if you do not want to increase the range of a car even further, there's a high incentive for OEMs to reduce the weight of the battery. So I think nickel-rich materials are for now the way to go. This might change in a couple of years when we have multiple product lines, maybe like different types of cells, high power, low cost, so on. So I think there's a lot of development needed. Right now, we're focused on the very high energy density, high power cell.
Great. Ulrike, you had one question from the crowd.
Yeah, I was starting to look a bit at the questions. We have over 35, which is a lot. So I'm trying to put some together. And I think the first one that I wanted to ask to our whole panel is around cell breathing, if you want. So the cell reversible cell swelling, the change due to lithium metal, and the pressure requirements at cells level. And as Jürgen, you were answering one of the questions, I talked also about what impact temperature could have. I think this was an interesting point that you had also on the lithium reaching nearly the liquid state, essentially, nearly fluid state. I don't know, want to start, maybe you want to give some highlights, Jürgen, from fundamental point of view, and then we go more application.
Yeah, I think, I mean, from the fundamental point of view, first of all, of course, all electrodes show volume changes. In the lithium-ion battery, you have volume changes of the active materials, maybe in the sum around 10%, which is manageable with the liquid environment of the typical lithium-ion batteries. In a solid state cell, of course, in a ceramic cell, this might already be critical. So that's why, of course, I would say these kind of semi-solid or whatever kind of concepts are attractive, or polymer concept as such. And if you go, of course, to lithium metal anodes, the volume effect is stronger. So that's why stack pressure definitely is an issue for any kind of solid state concept, and has to be considered. And I'm sure this is one of the reasons why also announcements for solid state batteries are always shifted a bit into the future, because not all issues are yet fully solved, I would say, at large scale. And with temperature, just as a final point, temperature, of course, may even be an advantage of a true solid state system, because liquids can solidify and then, of course, lose conductivity. But true solid electrolytes are solid. They can't freeze anymore, and there will not be a significant loss in conductivity if you go down with temperature. So one of the true advantages of true solid state batteries, let's say without any solvent liquid components or not jellified, may be really temperature stability at high and low temperatures. Of course, the best solid electrolytes are also reactive with active materials, and safety issues have to be considered. So solid state batteries, let's say ceramic solid state batteries, are not necessarily inherently safe. That is an issue that has to be also taken into account. Maybe all oxide batteries, maybe, but I would even that should be investigated.
I agree. And sorry for taking over. And then expanding on these points, maybe Francisco, if you want to start, and then Raymond talking a bit about these challenges with managing this particular KPI. And what's your view? What is realistic for commercial exploitation?
Just briefly on my side, the point is clear, and we all understand that not everything stops once you have the cell working, right? So the integration in a module, in a pack, particularly with lithium metal, is quite challenging because of the change of the volume of the cell, and the fact that the pressure is also evolving, right? So you have a certain pressure, a SOC 0, and you have a much higher pressure, a SOC 100. Right? So your mechanical envelope, right, in the pack need to be able to absorb all of this, while at the same time maintaining a minimum pressure that is high enough, so the cells are working properly. And at the same time, thermal management is very different from traditional lithium-ion batteries. So a lot of changes, which is making tricky, to enter in the market as a second supplier on an existing platform, because essentially you will need to change quite a lot of things in the vehicle platform to adapt to a semi-solid or a solid or this type of new technologies in there. A lot of work that can need to be done not just by a cell maker, but collectively by a cell maker and the customer.
Thank you, Raimund. Do you want to maybe expand on this?
Yeah, sure. I think so. Of course, working on semi-solid state, the pressure is less of an issue than for all solid state. But any additional pressure that you need on beyond the cell level will, of course, sacrifice energy density. So you have to make sure that your cell energy density is much higher compared to like the zero pressure application. But there's also a lot of know-how needed for the integration. So we've actually set up a dedicated module team to work on the integration and to better understand what are the limitations. I think it's always very important to look at the system level and not only at cell energy densities, as this might be confusing or like not fair in some cases. So it's a very important point and a challenge that we certainly also deal with. But it's another reason to go like this semi-solid alternative because you just need less pressure overall on the system.
Great, yeah, and you all touched on this topic as well, and I think let's move on a little bit more to the commercial side now of things and talking a little bit about the supply and cost topics. Jürgen, you mentioned, especially in your latest publication, that cost is proportional, obviously, to the lithium content in the solid state electrolyte.
Well,
Okay.
well, not proportional. I would say the other elements count too, right? So,
but definitely an effect, a big effect on cost there, right? And maybe you can expand a little bit on your point of view on how this technology, or what this technology needs to do to be cost competitive, because we all know the battery market is a very highly competitive, cost competitive market. And what's your thoughts on where this technology needs to go to compete with lithium ion here?
Well, I'm not a techno-economic specialist, but I would say at least when it comes to high fractions of true inorganic solid electrolytes in a battery with a considerable volume fraction of the electrolytes, let's say in the cathode, for example, then this additional cost of the lithium that in the electrolyte has to be taken into account. The funny thing is that if you think moving to a solid state sodium battery approach, I think the cost issue is not so significant. So the inorganic solid state battery might be even more attractive when it goes to sodium. But let's stay within lithium. That was just a side remark I would make. I don't know how significant that is. So, but if at the end every cent has to be squeezed out of I would say a cost calculus, then this might be an issue, of course. And then this is, of course, why I think all, I would say, the companies like Factorial or here or Buzzworld or Chinese and Asian players, of course, try to work on gel polymer concepts, because that's with a lithium ion concentration in the electrolyte that is as low as a normal liquid electrolyte. But this is, I think, not the true, reason for that. I think the true reason is that these cells simply work well, probably. And the only way, I think, for let's say, for those who really utilize ceramic solid electrolyte has to be better, to have true advantages compared to these other cells. That's probably the only way. They can't be cheaper.
Yeah, that's a good point. We will touch performance in a second, but maybe one comment from Francisco's side, since you showed that in the slides in the beginning as well. What's your plan at Buzzworld? How do you want to stay ahead of this competitive KPI with your technology?
Yeah, I think maybe I'm a little bit biased because I'm a car guy. I've been working in the car industry, in the mass market car industry for so many years. So for me, there is only one parameter that counts here, which is cost. There is only one, right? So if you get the current lithium-ion batteries, the ones we have now, with LFP or with NMC or whatever, and you get a 40% cost reduction, we will not be you and me talking around this topic here today, right? So the reason why we are here is because the batteries we have today in the market are too expensive for what the market can absorb. And we need something that is bringing a significant cost down. And I agree that if you have a lot of lithium with the current lithium prices, maybe cost down is not where you're going to land, right? So you need to reduce the amount of lithium as much as possible. And this is one of our biggest challenges. Get rid of all the excess of lithium by improving the efficiency of the product. But it's super clear in my mind, right? So there will be no breakthrough, commercial breakthrough of solid state if we are not demonstrating a path to a significant cost decrease.
Yeah, absolutely. Ulrico, you had some questions about performance, right?
Correct. Yes, I was again going through the question list. I think one recurring question from the audience is about C-rate, high power, and how to achieve it. I think Jürgen had some very good points that there is still no material to do that, essentially. So where do we think we stand today? Maybe we can start with Raymond, just to rotate. And what's the opinion of Factorial on how to achieve fast charge lithium metal and so on? What is the key?
The key to fast charging lithium metal? I think if we knew, that would be great. So fast charging lithium metal is fantastic. Is still like a big challenge. There are solutions that can be done on module and pack level. So I think there's still a lot of know-how needed about how to integrate the cell, how to acclimatize and condition the cell. So even lithium-ion batteries they usually operate at a lower performance at low temperatures or reduced temperatures. So it's not per se that this technology is good in every field. There's a lot more improvements needed, but I think you kind of have to get there to like the big cell stage or the product stage in order to improve on that. So as long as you have just lab scales and a lot of tolerances and not a very good reproducibility, it's very hard to do some fine tuning on the performance that would enable fast charging rates.
Maybe Jürgen, do you want to add something on this topic from more a fundamental point of view, or some of the strategies that you're envisioning? I think you're muted, sorry.
Yeah, sorry, I was muted. Yeah, I think the point is that we, in fact, don't know too much about charge transfer at the interfaces, really. So fundamental knowledge is not so well. So definitely we need to dive deeper into that to see what are really the kinetic issues, for example, with the lithium metal anode or a silicon anode in a solid state environment, which is very better investigated in the liquid environment. So that's, of course, why I think there's still lots of fundamental work being necessary to open up these perspectives for some that may, of course, at the end, as I agree with Francisco, of course, if there is no business case, things will not be done. Then if you have something that is good, but is probably not cost competitive with the lithium-ion battery, then you have to find ways to make it better. So then customers will probably accept price differences. So I think a significant part of work has to be really to improve systems such that they can be better in certain key performance indicators. And this is, of course, what we try to do. And I think kinetics can be something because there's no concentration polarization in the liquid or gel polymer electrolyte, which is restricting also the C rate very much, whereas the typical inorganic cell electrolytes are single ion conductors and there is no concentration polarization. We can show that lithium metal can be deposited and dissolved with amp per square centimeter rate, but there is morphological instabilities. We have to overcome that and we have to find ways to do that. So I think the only way is to enter really, I would say, into more the right side of my cartoons where it was more solid, let's say truly solid, is really intensified fundamental research to overcome these critical hurdles.
Yeah, thank you, Jürgen. Good point. And maybe looking at the time, let's spend the last couple of minutes on more questions that are coming more and more in the chat now about the commercialization of this technology. That's obviously what everybody is asking. Raimund, when do we see the first factorial battery in a car? And the same for you, Francisco. But let's look at this a little bit more sophisticated. So I think, first of all, it would be of interest to me to understand, do you see the EV market really as the entry market for your technology, or is there maybe other markets like aerospace where you really need high power, or potentially even the power tool market to try out and learn before going to the EV market? Or is the EV really the way to go? Raimund, maybe do you want to start?
Yes, so we talked to a lot of the adjacent market players aside from automotive, but ultimately I think automotive is the biggest market. So with all the capital that is needed to develop such batteries and bring it to a stage where they are relevant, I don't think there's a way around automotive for now. For us in particular, we have focused explicitly on automotive batteries, and this is of course not solely, but of course partially due to our investors. So our investors are mainly in the automotive space, and they really help us to scale up the product, to perfectionize the product. which is super important. And not, I mean, I constantly hear a lot of interesting applications and potential fits for solid-state battery, which might be a better fit short term. But if there's not a big market, then there's no money behind it to develop the technology towards that application. So I think for automotive, once you made it to automotive, a lot of other applications will benefit, but it's of course a big hurdle to get there.
Thank you, Francisco. What's your point of view here?
Well, pretty much the same. I think you need to consider that we still are extremely small companies, right? So when you cannot chase too many rabbits in parallel, you need to go to the big one. You need to catch the big rabbit because you don't have too many people. And at the end, entering in whatever application you can imagine requires a similar amount of effort, right? So in terms of development, your electrochemistry, adapting your electrochemistry, certifying, qualifying your process. So you will need to spend similar amount of time, whatever the application you have. So people will have a tendency to go first to the big rabbit.
Yeah, makes sense. And what do you think about size, form factor, cell to chassis, pack? What's your guess here? Like, are you guys staying with pouch formats or moving into maybe more of the prismatic? What is your take on the form factor here? Maybe Raimund?
So I think, so with regards to speed to market, I don't think there's enough time to develop like a cell-to-pack architecture for what we are targeting right now. And we're looking at 2026, 2027, which is a very short time frame, very big challenge for sure. So the first product will likely be a drop-in, I would say. Of course, there's many things to explore beyond the conventional module to pack, or like cell to module to pack approach. But again, you need a lot of experience, you need a lot of capacity, you need a lot of know-how in this field, and you also need to convince your partners that it's worth exploring this part. So I think naturally this is a more late-stage solution. Of course, this is all our vision. I mean, this is why we think that solid-state batteries have an advantage, because we get a lot of benefits beyond the cell. So, but we yet have to quantify those. We yet have to also demonstrate those. And I think this is, yeah, there will be like a more gradual adoption of the technology, just like from more logical point of view.
Yes, absolutely. Francisco, what's your point of view on the form factor? Will you be producing pouch cells first?
I think what I have learned in my experience with batteries, the form factor has become a kind of religion, right? So if you have one customer that only wants cylindrical, there is nothing you can tell them to change their mind. But what I also know, and I'm convinced as well, is the pouch format is not a good format for solid state. Maybe it's the one we need to go first because we have no time. If we have pressure to bring something to the market quickly, as Raymond would say, I mean, changing the cell format and moving into cell to pack is with the size of companies we have now, I mean, it's not going to happen. It's not going to happen in the short term. But moving forward, I see prismatic and cylindrical much more interesting form factors for the type of product we have than pouch.
Awesome, really interesting. Great discussion, guys. So maybe looking at the time, last topic I want to touch on is the data topic, and maybe a question to you, Jürgen. Data is very important in the academic field, as we have learned from one of your papers where you were comparing solid-state battery performances in published, scientifically, academically published papers, but also in the industrial side, right? And this is a lot of feedback we are getting from our commercial customers, that for them it's really tough to judge which of these technologies is at which level, because there is so little data out there. And I would really like, in the end of this webinar, now highlight this point of of kind of understandable, comprehensive data, both from an academic, Jürgen, this question to you, but also from a industrial point of view later for Raimund and for Francisco?
Well, I think the first point I would make is that probably the data we see on solid-state batteries maybe is only 1% of the data that are existing, because the industrial data we don't see. The academic data, of course, are usually a small number of cells, large scattering probably, because of course the academic labs are not optimized for, I would say, a serial production of cells. So when it comes to data, and the question always of data mining and everything and data analysis, this of course requires huge data sets, and industry have them, and not academia. So I think that's why academia cannot be too successful in that respect. We can, of course, compare these data sets, and as you said, already at that time, I think that was two to 3 years ago, it was very difficult to analyze the data sets, because almost any paper had not a complete reporting of all data you needed to make a full analysis. So that's, I think, the first thing I would really ask is, at least those labs who can publish data should publish complete data sets. I think that I think is something which is nice. And well, of course, I think this is probably only a hope that industrial players publish more real and complete data. Then things, I think, would probably be much better. And then also industry could be a better guidance also for academia. Right now, I think, I would say, as I said originally, I think there is not a proper, I would say, bidirectional communication between industry and academia. So there is also no reason for industry to complain about academia. As long as they don't give more information, things will go on as they are.
Yeah, good point, Jürgen. Couldn't agree more. And maybe here a little bit of advertisement. Check out our website. We produce amazing test equipment for solid-state batteries. So if you want to produce good data, check this out. And maybe now over to you for the final question, Raimund and Francisco. What can we do from a industrial perspective regarding this data topic? Jürgen mentioned that it's difficult because they don't have a lot of data. There's not a lot of data published. On the other side, you guys need to protect your IP. You're in the development phase. We're in this kind of turmoil here. What's your take on this, Raimund? How should we proceed here? And what are probably first steps or solutions towards that?
Yeah, so I think first of all, I hope that academia is not mad at industry particularly, and the other way around. I understand that there's a lot of scientific curiosity about what is being done in industry. But from an industry point of view and from a commercial point of view, you always have to ask yourself, why do you want to share data? What's the benefit to the company? So do you just want to tell your competitors where you are? Do you want to advertise the company? And the truth is, it's an ongoing development. So if technology was ready today, it would be in a vehicle today. So the expectations are very, very high. The chances are that the data you will show will still never be enough. So you have to be very selective with what you want to show and for what particular reason. But then again, as you mentioned, a lot of the innovations are usually coming from academia, and then they're kind of like perfectionized in the industry or maybe behind closed doors. So I can only speak for Factorial. So we collaborate with academia a lot. So we have a couple of development projects, not only with OEMs, but also with professors and academia. Where of course we source from academia, we have to provide data, because if you do not provide any data, you can't ask someone to solve your problem. So not publicly, but we do it.
Great. Awesome. Francisco, what's your take?
So first of all, my little contribution, I think that in Europe, we're not doing anywhere near enough in academia about this topic. We need more researchers, we need more people doing fundamental research. It's a bit selfish because, I mean, you know, for me, this energy transition should be a way of Europe of reclaiming industrial leadership and getting back to the top position that we had in the past in Germany and France, in Italy. We were all super proud of being industry leaders. Now we are losing that. And I feel we are losing that because we have not invested enough, early enough and enough in academia, in researching, not just lithium batteries, lithium-ion batteries that we have now, but what's coming next, right? And the way of launching companies and the way of creating new industries and services always start with somebody in academia. Because they are the ones that have the time to think, right? And then to research and to understand things. And then we come us on top and we add industrial layers and seeing how this understanding, this knowledge that was developed here can translate into something we can sell to people, generating value and jobs, you know, and economic value for everybody. So we're not doing enough. And I think there is not much I can do other than complain, as you can imagine. But we think we should invest much more from Europe and from member states in academia. And that would also indirectly solve the data issue. Because if we get more resources, more people searching, better interaction between technology players and academia, we're going to have a little bit more information that is publicly available. Having that said, I mean, it's true that from the moment you are entering into the competition area, you need to maintain your secrecy, at least until you have commercialized that product. But the baseline, you know, the non-competitive area in Europe is absolutely nowhere near that it needs to be for Europe to be, you know, maintaining and claiming this leadership position that we should have.
Yeah, great to hear. I mean, ambitions and big visions everywhere, right? Not only in the industrial side, but also the academia needs to support and is supporting, as we can see from Jürgen's slides earlier, right? A massive network and collaborations are being built up there. Guys, we're coming to the end of the webinar. It was a really, really big pleasure. I have a final question for you, a personal question. You don't need to answer from a, let's say, political and from a industrial point of view, just your personal opinion. When do we see the first commercial solid-state battery vehicle driving on the road in Boston, in Paris, or in Germany? Jürgen, let's start with you.
Oh, that's you asked the right person. Well, I'm always an optimist. I think I'm pretty sure that Raimund will be successful and Francisco. So I think if we consider gel polymer batteries as solid-state batteries, I think that's definitely something we will see. I'm pretty sure. I would say I would be surprised if they would be cheaper than lithium-ion batteries, but this is something probably I will squeeze into the panelists maybe later after the discussion. But yeah, so I'm optimistic about that.
If they are not cheaper, you're not going to see them.
Yes, exactly.
Francisco, what's your date? When do we see the first car?
Well, honestly, I'm also a very optimistic person. I do believe not only us, but there will be also some of our competitors. The sooner I think we can do it is 2028. I don't see how you can have a real car in the street. Right? So you need to start your production obviously before, but going through the whole process takes time. So I hope that by 2028 we have the first cars with advanced solid or semi-solid batteries out there.
Awesome. Raimund?
Yeah, I feel like I've answered this question before, but I think you also have to differentiate, is it a serious production car, or is it like a demo vehicle, is it like a small fleet, and so on? So I think production car, more like what we've talked about before, but probably before that, you kind of want to do some field testing and maybe some showcasing of your technology. So hopefully before 2027.
Awesome. Fantastic. Ulrico, what's your point on that as a last comment?
I think if you look at some of the semi-solid or like mostly liquid, let's say, it's hard to say, it will be the next couple of years, maybe around 25, 26 even, but truly solid state, I think it's towards 2030, to be honest.
Awesome. So only optimists in this panel today. Really appreciate it. Thanks a lot, guys, for your time. To all the participants, also, thanks a lot for your questions that you submitted so rigorously in the chat. There will be a quick feedback questionnaire popping up in your window now. If you take 1 minute to fill that in, that will help us to become better and improve our sessions. With that, thanks a lot again to Jürgen, Raimund, Francisco, and Ulrico for joining us today. Was a really big pleasure and hope to see you soon. Thanks a lot for your time.
Yes, my pleasure. Thank you.
Thank you.
Bye-bye.
Thank you, guys.